Hey, welcome everybody. My name is Jim Radigan. I'm an architect for the C++ team for compilers and runtimes. And I do some stuff on many other parts of DevDiv, as well as some security work. So today we're going to talk about memory safety and how important it is. We're going to talk about basically why it continues to dominate. So memory safety, 2018, these were the statistics for what we internally measured for CVEs. And as you can see by patch year, the CVEs continued to grow. And when you look at the root cause of all that, you can see that type safety really was a big issue. Memory safety was 70% of all the CVEs that we measured in that. So in 2019, I did a talk. We released the address sanitizer. And then I was invited to do this talk. And in 2021, here's where we are now. So 6 in the top 25 are still memory safety issues. So if we zoom in, can you guys read that? It's, you can see that number 1 and number 2 are classics, and they've actually gone up in popularity. And the other one is use after free, followed by an integer overflow, null pointer dereferences, and improper range checks that were manually written. So I showed this to my son, who just graduated from computer science at Illinois, and I asked him for some insights, and he said, man, your first talk must have really been blown. So here we are today, and what I'm going to try to talk about is, or emphasize, is why memory safety is so important. And then I'm going to try to talk about a new tool that we're introducing for you guys to use. So from a high level, this really looks like, what are the bad guys doing to make this so important? And then we're the good guys, we're going to give you a new tool. But the one thing that I really want to emphasize is, I think that I really thought about why the memory safety issues have not gone down. And I believe it's because nobody's shown you what the bad guys can do. So a big part of this talk in the beginning is I'm going to try to show you what they can do. So for the bad guys, they have invented programming paradigms. So return-oriented programming is the first one. That was the oldest one that's been around for a while. And I'll show you some really great papers from 2007. Data-oriented programming, block-oriented programming, and direct data manipulation are the new mainstays. So what happened was we sort of thwarted them on the ROP a little bit with some of the secure code generation work, and they moved on, and everything's about data. So if you can, I just highly recommend that you read one of these papers. That literally was written, the top one, 2007, and the geometry of innocent flesh on the bone returned into libc without function calls talks about what ROP programming is. And return-oriented programming is basically a whole new paradigm of just changing the return pointer to go where you want and then moving the stack pointer. So you move the stack pointer, change the return pointer. Move the stack pointer, change the return pointer. Now you have a new way of programming a computer. So I'm going to start with a traditional chunk of assembly language. It's really simple to see. It's just 3 instructions. The green are just the registers on the machine, x86, and then the yellow is the stack. There's the stack pointer pointing to val1, and A1, A2, and A3 are just the addresses of those assembly language instructions. So if we start at A1, the instruction pointer's at A1. We load val1 when we execute that. We move on to A2, and now what we're going to do is we're going to load val2 into EBX and move to A3, and now what we're going to do is basically that store. It's very straightforward. Now I'm going to show you the next slide. You can program the machine to do exactly the same thing in a completely different way. And this is what we call a constant gadget. And so we're going to accomplish the same assignment, but we're going to do it with using the return pointer and moving the stack pointer. So we start out at A1, we pop, we get val1 into EAX. We execute the return, we go here. Then we get to A3. Remember the stack pointer moved, and now we're at A3. We execute that to pop EBX. We move on to A4. We do the return. The return is going to take us to A5 because the stack pointer is one slot below. So we move the stack pointer, and we're here at the final instruction, and that's going to carry out the assignment as well. So what I can do is I can program anything with moving the stack pointer and modifying where the return is going to go. I can string these gadgets together, so there's 3 different gadgets. I can string them together to actually accomplish a more interesting program using an infinite number of gadgets, actually. And so what that gives you is return-oriented programming is actually provably Turing complete. It's usually Turing complete, and it can do any kind of arithmetic operation, logic, conditionals, loops, subroutines, call existing functions, call system calls. But sometimes when it's thwarted, it can actually just run straight line code and get far enough along to invoke a system call. It all starts with one memory safety error. You can imagine it, right? If you just actually write to the stack somewhere that you shouldn't and you hit the return PC, that's where you're going to go when you execute the return instruction. So what's memory safety? So that's a long list of what memory safety is. You'll hear all sorts of textual definitions of this in the English language, and none of it really does it justice. The only thing that I can think of that would organize these is that there's a temporal aspect to this and a spatial aspect to it. And one of the things that we did is we tried really hard to document this. So every one of these errors will take you to a classic error, classic heap buffer overflow example that's compilable. And then we can show you from that web page how we've integrated in the address sanitizer into the IDE to find that particular type of memory safety error. And we do that for every single one of those things that I just listed on the slide for you. So each one of these has at least 3 or 4 examples that will compile, as well as what will happen when Visual Studio encounters one of these if you've been using the address sanitizer. The neat thing is that with the address sanitizer, which is a simple recompile, you'll find all of these with 0 false positives. So if you're a programmer, you're thinking, well, what can I do? And that's the Microsoft security stack. One of the things I wanted to do was apologize to all the users and the developers for Microsoft, because nobody has ever put a diagram together like that to describe all the security technologies that we've developed at Microsoft. So at the top, you see there's source modifications. We've got GSL and attributes and pragmas that people might have used in the room. The two circles in the middle of the Venn diagram talk about static analysis and dynamic analysis. And then finally, something not everybody might be aware of is the bottom part of that Venn diagram is where the compiler actually does secure code generation. And we'll get to that. So what's secure code generation? The reason I'm going to show you this is that we did secure code generation, 2 iterations of it, and got all of Windows and the hypervisor compiled with this. And it thwarted ROP for a little bit with the first version, and a lot with the second version. I'll go into that. But then it moved everybody into trying to manipulate data, which then is a great history and a lead-in for the address sanitizer. So with CFG, which was secure code generation, what would happen is an indirect function pointer could only go to targets that the compiler generated. So we would generate code with that flag and make sure every indirect function call went to something the compiler created. And same thing for C++. Everything was compiler generated. So that's the assembly language view of what was going on. Basically, we would call through an OS loader primitive. We would load RAX, and it would go do the check to make sure that that symbol function was something that was put in a table by the linker. And if it wasn't, it would just pull your process down. Boom. So that was not, as you saw in the previous slide, it wasn't that selective. It was every indirect call could go to any compiler-generated target, so we tightened it up. Now that can only go to something that has a matching signature, and that can only go to something in C++, which has a matching signature. And this really tightened things up, and this is what the newer code generation looks like. So before, we would just load RAX for where we were going. But now what you can see is we also move into R10, a compiler-generated hash, which is unique. And then on the other side at the target, that compiler-generated hash is there, and the function prolog will actually check to make sure. So we talked about secure code generation, which was down in there. But just to give you guys an idea, we spent 10 years on control flow integrity, and you'll see a CFI is thrown about a lot for basically any means to control or to ensure control flow integrity. And ROP is one of the most heinous attacks for violating control flow. So we did a lot in that space, and it really it bothered the bad guys. And the paper there in blue is something that was from 2018. So the good guys versus the bad guys is still progressing, and this technology gets more and more interesting. But what happened was it got harder to actually do ROP attacks. And so they moved on to newer data-oriented attacks. And data-oriented attacks will manipulate non-controlled data. So a variable or a pointer which does not contain a target address is what is usually the thing that gets manipulated. And what happens then is it just changes benign behaviors in parts of your program. And it does all of this without violating any of the control flow. So your program, pieces of your program will be manipulated, and it'll go through existing control flow paths and execute entire basic blocks. So an example for a data-oriented attack is just simply flipping a bit in a variable. So the data-oriented attacks are broken into two categories: data-oriented programming and direct data manipulation. And BOP, or block-oriented programming, is a special case of data-oriented programming. And I'm going to show you an example of a BOP attack and the tools that they use. There's actually a compiler for this, so it's called Sploit. And this is a simple exploit program that the bad guys would use. What will happen is the compiler will take this and it will actually use that to generate all of the actions that are needed to figure out how to get pieces of your program to carry out those instructions. So if you remember, I'm just going to show you quickly. Those are the 3 lines that do the simple assignments, and this should be easy to follow along. So what they do is they disassemble the entire binary, and they'll look for pieces of functions that actually form a tree, not what we call an acyclic graph. And so what you can see is those assignments that I actually filled in those blocks are candidates for running that program. So what they do is they name those because they know they're real candidates. And then we have the problem of how do we actually do register allocation for the user's local variables R0 through R2. So first, they create a graph with all of these potential basic blocks to carry out those statements in the program. So the first line has a possible choice for choosing 2 blocks in your program. The second line is 3. And the third line in the program, you can use those 2 basic blocks. So then what it does is it says, okay, given those statements, what's the conflict graph? It builds that conflict graph and it says, okay, there's a binding. What I'm going to do is I'm going to map RAX to R0, RBX to R1, RCX to R2, and now all we have to do is figure out what's the path. And you remember, we numbered the blocks that we thought were going to be candidates, 1, 2, and 4. And so the red lines actually show a path that this compiler is going to have to make happen in your program, in your existing binary. So the red is the path that's going to have to be taken. And the blocks that don't contain anything are considered dispatcher blocks. And what happens is this tool is so sophisticated, it will symbolically execute the dispatcher blocks, and then it will actually produce a write, what, where list. So it all starts here. That payload is loaded into your thread or your executable at runtime because of a memory safety issue. So the bad guys, so we call these memory safety errors, but the bad guys actually call these arbitrary write primitives. And they actually sell these. You can go on different parts of the internet and find out where there are existing known memory safety errors. So here's a real, I'm not going to get in trouble because these are older exploits. I had to change the deck. So this was a very famous exploit for a while ago, maybe about, I would say, 8 years ago. The Windows Movie Maker, this was a heap buffer overflow vulnerability. Can you guys see that? Is that color choice doesn't work, I guess. Now, So what will happen here is the variable CB size will get 4470 as a size. We'll allocate a buffer that's 4,470 bytes wide. Then CB size gets reassigned, and then boom, that's a heap buffer overflow right there. This is SQL Slammer. This is a stack overflow. This one was really popular. That's an instance of a named read from a socket. And then here we actually get a stack buffer overflow, and then the hijack hits the return address. I'm going to show you a use after free. Here's what the victim, attacker, victim dialogue is, if you will, in a scenario. On the first line, the victim's going to delete an object. On the second line, after the object's deleted, they know when they can do what we call a heap spray. And what they'll do is they'll go in and just spray whatever number they're hoping to, a target address that they're hoping to hit. And they're indiscriminate. They'll go across the entire vtable for that dead object, or an entire page in the heap, actually. And then what will happen is, finally at the bottom, when you have your erroneous call through a dangling pointer, you're going to invoke the bad guy's code because the vtable got sprayed. And that's exactly what happened to Internet Explorer many, many different ways. So we're going to pass an onload event, we're going to copy it, and we're going to fail to do an add ref. And so what's going to happen here, I don't want you to have to struggle through this, is basically F2 is going to be called asynchronously. If you could see at the bottom of F1, there's a call to set an interval of 50, and by that time, parts of E1 have gone out of scope, and the vtable got hijacked. And this is something that happened all over Internet Explorer because of the need to be able to be so flexible and allow any kind of plugin you could imagine. So there were so many attacks like this. Basically, what's happened is that the nation-state actors are experiencing a hiring crisis. It's getting so bad. So, really, how bad is it? Well, they're here. The government's here. This document went out in spring. This is what's required for shipping software to the government. And it's going to be changed and modified, and we're going to be responding to it, and this is going to grow. And it's guidelines on minimum standards for developer verification of software. It's what you have to do, and you're going to have to certify that you do it. So, in answer to the question, that's how bad it's getting. The government's involved. So we talked about the bad guys. Now I'm going to talk about the good guys. And if I could ever get one message across that's so important, it's that static analysis and dynamic analysis are absolutely required to deliver C++. Full stop. So static analysis you might be familiar with from /analyze, and dynamic analysis is the address sanitizer. You can think of it as static analysis takes place at compile time, and dynamic analysis takes place at runtime. So I'm going to do a quick demo. I want to actually show you static analysis and dynamic analysis all in the same program. So if you can see this has been brought up in the IDE, and we've got every static checking rule available. And you can see the green squiggles, I hope. And if you step on the, if you put the mouse on the green squiggles, you can actually see the different warnings that the static analysis will provide for you everywhere throughout the program. Question? Oh, yeah. I think I can. There we go. How's that? So I can't get the pop-up, though. I can read it to you. Function work with delete can be declared no except. This thing is saying do not delete a raw pointer. And then this is saying avoid calling new and delete explicitly. And then this is saying move, copy, reassign, or reset of a local smart pointer B1. So those are all warnings that you would get using the static analysis. Now, if I use dynamic analysis for that exact same example, it's going to actually show you what is a true memory safety error. So if I just run this, boom. And what you find here is that the deallocation size is different from the allocation size. And what that really means is there's no virtual destructor. And that's a memory leak, and that leaves a spot. So static analysis and dynamic analysis have different strengths and different things that they can look for, but the address sanitizer has the win of when you pop one of these bugs, there's 0 false positives. So there are limits to static analysis at compile time, and there's a lot of noise, and it's theoretical. It's not an implementation detail. If you think about it, that's a virtual function call, and we don't know where that's going to go if we don't know what the type of the pointer is. We don't know what P points to. And if you're doing alias analysis, you see star Q preceding P, you have to assume that most of the time that's going to kill what we think is in P, so we're not going to know what this function call can do. And likewise, since we don't know what that function call can do, we don't know what its side effects are going to be to the alias information. So there's a cycle. So alias analysis and type propagation statically are locked in an infinite cycle. And that's why there are limitations, and that's why there's noise. So with the address sanitizer, or dynamic analysis, what we're talking about is a simple recompile. You're just going to add a compiler flag to the existing flags that you already have. We made it so that this would work with O2, O2GL, O1, OD. So this has 2 basic techniques. It has runtime tests that are inserted before every memory reference by the compiler. And then everything in the CRT and the RTL that has to do with memory allocation gets hooked, or it's like malware. What happens is the address sanitizer, when it initializes, will come in and forward calls to like malloc and delete to its internal implementations of those. You don't change your program. The compiler doesn't have to do anything. It just immediately does the intercept or hooking. The important thing, too, is not only are the allocators and deallocators hooked, but things like memset and memcopy and stir ncopy and other heap operators are also hooked. So what happens is the runtime actually creates an entire closed universe as far as any dynamic memory that's been allocated. So I'm going to give you a simple idea of what's happening on the test side that's inserted by the compiler. Basically, at a high level, if on the left-hand side you see a store, what the compiler is going to do is insert code to precede that store with a check against a shadow byte. And what's going to happen is if that shadow byte says that that pointer is not allowed to be accessed at this point, it's going to do an elaborate report, and then your entire program dies. So this is what shadow bytes are all about, and this will be really quick, but it'll ground you for what the address sanitizer is all about. So on the left, each one of those rows represents 8 bytes in your application. And then on the right, each one of those is a byte, and those are the shadow bytes. So with 1 byte, I can describe what's going to be allowable in terms of access for 8 bytes in your space. And I can use positive integers to say what's accessible, and then I can get really clever about negative numbers to tell you, well, not only is it not accessible, but there's a reason why. So what'll happen is these can change at runtime, and the compiler will generate code to change these, and the runtime will generate code. And so what'll happen is that F8 will change to a 4, and F8 before really translates to out of scope. And then those get overwritten, and that entire slot in the memory space is no longer in scope. And the compiler and the runtime are constantly hitting these shadow bytes while your program is executing, and before every load and store, it's checking the shadow bytes. So runtime hooking provides amazingly powerful functionalities. So if you think about it, this is a visual for what the asan init function will do. If you call malloc, you would just go call into the CRT and you would execute the body. But after asan init, what happens is you get forwarded to the asan version of that work. It'll jump back into malloc, and then that'll return. And the first couple of bytes that are overwritten in malloc get executed upon entry to the asan malloc. That's exactly malware. There are 4 different techniques for this. One of them uses detours. But this is an incredibly powerful thing, and there's no overhead to the compiler or to the programmer. You don't change your source, and the compiler doesn't have to do any extra checking. So, for example, if you add memcopy, the compiler doesn't have to check any of the pointer arithmetic that's involved. All the checks are buried in the memcopy. So it's incredibly powerful because it also allows both the compiler and the runtime itself to know the size of every dynamic allocation. I can go from any pointer that was allocated in the heap and get a whole bunch of metadata. One of them is the size, and that's incredibly important. You get complete call stacks for every allocation, so that when there's an error, you can say, what was the call stack when this was allocated, and what was the call stack when this was deallocated? And there are built-in checks for all the arguments for all of the CRT routines that are memcopy, stir-in, copy, memset, the whole family. There's about 27 of these. And then also there's an implicit initialization that takes place, which is incredibly important. So if you allocate a node and it's got a pointer in it, the compiler doesn't have to worry about initializing it. It's going to get initialized to 0. So dynamic analysis is just a simple recompile, and the address sanitizer consists mainly of these 3 things. Compile in runtime checks, you link to the address sanitizer library, you run your program, and then it'll The address sanitizer library will do an exquisite job of diagnosing exactly what the errors are. The only problem with this, like static analysis has problems, dynamic analysis needs to be run over a very large code base, or to use the fuzzer, because you've got to guarantee that all the code paths execute to prove that you found the memory safety errors. Now, the problem with the old address sanitizer was that it was a one and done model. If it found a memory safety error, it would report everything and then it would die. So one and done is what we called that, and that's amazingly disruptive to anybody who has an existing fleet of machines that are doing tests. So say there are some of our ISVs and Office who have over 200,000 tests that they run, and they're all distributed. So the first time you throw the address sanitizer on, it's like throwing a grenade into this whole test lab, and it costs a lot of money. So if you disrupt because of just one and done, what everybody wanted us to do was change it so that the address sanitizer could just continue on any error. And what we did is we made it so it would log the errors to a log file, and then all your expected results would still continue. So your tests would pass like they do today, but all the memory safety errors would be logged. And that's not intuitive if you think about it. The problem is so many programs are running test suites every day and they don't show the memory safety errors. That's why this tool is so important. Every time we throw the address sanitizer on a new program and let it run its tests, we see tons of errors. So the new ASAN runtime, just think of it as a new OD compiler. I want to take 1 second and just call a shout out to the team back in Redmond. Amy did a tremendous amount of work on deadlocks that we had to deal with, and Zach has joined us and done a lot of work on interop. Kemi is all about getting us into LLVM 11. And Mahmoud is a manager that's helping manage resources for this team, and Bran is helping out with the compiler. And this team is growing because there's just so much work to do and there's so much demand for this. So the major changes that are going on in the runtime are interop on the Windows platform and then continue on error. And interop on the Windows platform is an enormous problem space. You have to work with managed languages. Memory can be allocated before your process starts. You got to be able to handle multiple DLLs. It goes on. And then continue on error was pretty tough because we actually had to move metadata around, and I'll get to that. So on the Windows platform, we've introduced an improved awareness of Windows allocators. We intercept RTL allocators. We have up-to-date interceptors for Windows. When I showed you that malware example, when the compiler changes function prologs, the address sanitizer has to be in sync with that. And so XFG, which I showed you before, was modifying the prologs, and we had to actually immediately update the address sanitizer so that it could properly hook functions in something that had been compiled with that secure code generation. And then we did a tremendous amount of work for improved compatibility with DLLs. The biggest one was being able to detect allocations that had taken place before the address sanitizer started. And we call those wild pointers. And the issue is you can't check the shadow bytes for something that hasn't been allocated in your process, because the address sanitizer is tracking every single allocation, and it's got metadata associated with each of these. And so one of the things we had to do was actually scan all the heaps that were already allocated, had already allocated storage, and then create a really quick data structure for lookup to see whether or not the pointer was truly allocated in an existing heap before ASAN. And then one of the other things that we found was we had to actually deal with the override of the import address table. So graphics drivers are really prone to this. They will actually overwrite the IAT entries for allocators so that things actually happen automatically on the card, on the memory, on the graphics card. And the address sanitizer is really critical for testing drivers. So we hooked or intercepted extra APIs. The thing that is traditional is that everybody uses malloc and free and calloc or operator new and delete. But on Windows, especially because of a massive amount of legacy code, we had to hook the RTL layer. So we had to add the ability to hook the RTL allocator and free and RTL size heap and RTL destroy heap. And that caused a lot of problems. So I wanted to say that the two problems are wild pointers and deadlock. That's what happened as soon as we hooked the RTL allocators. And I'm going to step through this just to give you a taste of what it looks like. So we hook RTL free heap, which goes to the forwarded RTL free heap in the ASAN runtime. We take a lock to try and actually see who owns that pointer. We call RTL free heap, and right here at number 4 is the new thing. When you're using the RTL allocators, they're built on top of the low fragmentation heap by default. And the low fragmentation heap is going to return the block to use, and what's going to happen is it frees an internal bookkeeping node, which is a pointer to God knows where. So what would happen then, we'd come over here to steps 6 and 7, try to determine ownership, take that lock, and then ASAN would erroneously assert a wild pointer. So in order to get through this, we actually had to add 2 locks so that there are a total of 3 locks to make sure that everything is working okay. It took us about 3 months to get that right. And those are the gory details of what they do. But I wanted to give you a status. So given all of that work, what's happening is the compiler will run 185 OSS projects on a weekly basis. For ASAN, we're currently running 148 OSS projects on x86 and x64. And we've got a blog up that talks about bugs that we found in Boost, OpenSSL, and the Azure IoT SDK. But then when I look through what our current status is, I think that's 27 open source projects where we found a bug and we have not been able to find the time to go in and change those projects and fix the bugs. But we just started, and so we're going to be communicating a lot about all the fixes that go in. So when we do the new continue on error, one of the things that was a problem was the LLVM symbolizer. We had to eliminate it, basically. And then we had to handle clobbering of ASAN metadata. Remember, the bad writes now will execute. Before, you would check the shadow byte and you would pull down the process. Now, we're going to report an error, but we're going to continue. So all the bad, evil writes are going to go wherever. And a lot of times what was happening is we found out painfully these writes would clobber the metadata in the runtime. So to get rid of the symbolizer, this is a visualization of what I think is an important thing to walk away with. At first, the ASAN runtime would take, when it was reporting an error, would actually call across a socket to LLVM symbolizer.exe to symbolize every single entry symbol in the call stack. And then it would return back the string for that. So in this particular case, if you want to deploy the address sanitizer as just an extension of the CRT and run continue on error, you can't have another executable around to make it really hard to distribute this. Plus, that's incredibly slow. That's okay if you're doing one and done, but if you're going to continue on error, this is a killer. So what we did is basically folded that functionality into the ASAN runtime using DBG help, and now what you have is a CRT for memory safety. We got rid of that, and this can be deployed now. It's almost invisible to anybody that there's actually a new runtime. So bad writes now will clobber. So in this particular case, this is an underflow. And so what's going to happen is that a sub minus 1, we're going to write pi into a sub minus 1, and what that does is it actually hits exactly the core metadata for the allocation A. So we're going to go from die to report and continue and take the hit. So what we had to do was move all the heap metadata and change error reporting in order to get the address sanitizer runtime to be robust enough to continue on all errors. It had to basically handle every erroneous write. So the guarantee is going to be that your program will run. If your program ran before with memory safety errors and there was no real undefined behavior, it'll still run. We'll log silently all of the memory safety errors, and you'll get an expected output. So that's a visual. I don't expect anybody to remember this, but you can see those are 3 different sized allocations, and the big box to the right is the user data. And then everything to the left of user data is some form of metadata. And most of the metadata that's there is to help with error reporting, but also to tell you if you've got a pointer, where are you? So I just wanted to quickly give you a demo of the GCC compiler. So I ran this, and it takes forever because it has over 1,000 errors. So if you use the GCC compiler as a test case itself, that's what it's going to output. And we will actually write that summary for you, and I probably need to zoom in on that one. Is there a zoom on that? Oh, I'm sorry, I can't zoom in on that. But what that gives you is an organized list of 1,000 errors, first telling you that all of the errors are going to happen in 3 files. And then in a prioritized way, it's going to tell you each function and then at each line, and it's going to give you the hit count. So you can actually digest this information quickly. I guess I could cut it, but I don't have time. So now, just to show you the comparison, if I turn off the option for continue on error, and I run this program, The program, I'm going to invoke the GCC compiler compiled with ASAN, and it's going to produce an assembly listing. And what happens is you'll see that it dies immediately parsing the command line. So if you ran that and one undone, you're like, oh, I don't have a lot of work to do. It turns out I think it was 1,033 errors in the GCC compiler. That was an old version of GCC right after they started to port to 64 bits and then the 2017 version of GCC didn't have any memory safety errors. So for extra work that we're doing right now, we're going to have improved compatibility with mixed mode DLLs. Everything, on Windows, everything's done with DLLs. You can have probably, like Tencent had an application with over 100 DLLs. And so some are built with the static version of the CRT. Some are done with the dynamic version of the CRT. They load and unload the DLLs. And some are compiled with and without ASAN. So we had to be incredibly resourceful to figure out how to handle all of those scenarios, and we're going to continue to be more resourceful. And then we have to have compatibility with all managed code. So the Microsoft platform uses a lot of C#, and then C++ CLI, or the newer version of managed C++. Now, on the compiler side, when I do a profile, what's going to happen as this approach is being used as an OD compiler, we had to look at the performance. And I think, if you guys can see that, at least this I can magnify. That's the top of the profile. So you can see what's happening is, what's dominating the performance, both for Xilinx, which is an XML parser, and GCC, which is a regular compiler, are the runtime tests that the compiler's inserted. And also, number 2 is capture, stack, traceback. And the reason that is because, again, the error reporting was meant to be incredibly helpful to anybody that hit an error. And what happened was every allocation did a complete stack traceback, and then every deallocation did a complete stack traceback. So if you can think about it, every time you're generating work lists for the DOM in Xilinx parsing the XML, or you're building a flow graph with IL in the compiler, you are just constantly allocating little nodes and constantly walking the stack, and then also you're constantly doing runtime tests. So the way we're going to address this is we're going to have to do an escape analysis. Everything works right now with every level of optimization, but we're going to have to do escape analysis, and we figured that that'll get rid of 50% of the local runtime checks. Range check elimination is a traditional JIT optimization. So basically you can pull these runtime checks out of a loop and do one big giant range check at the top, or you can find a place where a check will dominate. And then the other one, which is really complex, I wish I could have gone into it, we handle hidden updates. If you have star P pointing to something or double indirections, you could possibly be changing what a previous pointer pointed to right out from underneath you. And we build a points to graph from that, and then we use the notion of a hidden update to drive how we're going to mark tests that have to remain. We're going to build on top of one other thing here, which is some work that Chris Latner did in 2005 and Konstantin did in 2012. And it's almost like I wish this work were you could reverse the dates. Like if the work that was done at Illinois by Chris Latner had the runtime checks available in 2012, 2005, then I really think you would wind up getting something close to what we're about to do. The key is footnote 1 in that paper, and that paper is really excellent on the top. But basically, they did a type-safe C++ compiler, or C compiler, and they did it without garbage collection and without any language restrictions. And they say in there, in footnote 1, future work will be to handle arbitrary C++ and the insertion of more complex runtime checks. So I found this paper 2 weeks ago, and I just wanted to call out, these guys have thought about this stuff way before I did, and we're going to be shipping this. So it was a good feeling of validation, but also I want to call out these two guys. So this is one simple addition, which is we're going to initialize any pointer to null before any use. And any use means that we took the address of it. So any pointer that's being passed into anything else is going to be guaranteed to be null. And then the other thing is we're going to add C# type system rules through compiler optimization strategies. We're going to try to make it so that no local address can be returned by a function and no local address can be stored to a heap or a global variable. And when we can't make those guarantees, we'll fall back onto inserting the runtime checks. So CL-memory safe is going to basically be optimization of runtime checks, optimization of runtime metadata, and we're going to reduce the memory usage, basically from using the existing optimizer, which has not been enlightened for a lot of the runtime checks that we've seen from analysis. And then the runtime is going to have a massive amount of interop to support the Windows platform, and we're going to have the ability to switch between one and done or continue on error, so you can deploy however you want. But since the continue on error is going to have less runtime metadata, the reports are going to be a lot slimmer, so that the continue on error could be faster. And then you'll be able to fall back to the original one and done and get the complete rich giant screen for the error reporting. So in a way, you can think of this as CLOD with runtime checks, only a lot better runtime checks than you currently get with RTC. So we can't change the statistics about memory safety errors and all the exploits without you. It's so important, if anything, that you walk away with the single message that memory safety is critically important. And I tried to show you what the bad guys can do in a very limited amount of time. I didn't show you any of the tools that are actually for sale that are industrial strength. That was the compiler for Sploit that I showed you was academic, and it's on GitHub. And then, because this is so important, we're doing Address Sanitizer 2.0 with continue on error, because we got the feedback from customers that it was so hard to deploy when it was one and done. We were basically blowing up test labs because nothing would work on the first turn. So, anybody build on code here that's older than 2 years? Okay. What's the level of memory safety in the code that you're using? I know everybody in this room is building on code that's at least 2 years old. And you probably don't even know. So, questions or comments? I got 64 seconds.
Hello. Great work. Thank you for presenting it. My question is, you mentioned a blog where you'll be posting updates as you were preparing this for release. So what's the approximate time frame and what's the URL of the blog?
So the date for the first release of this is November 8th. That's going to be 17.5 Preview 1 of Visual Studio 2022. The blog is going to go up probably at the same time. One of the other things that we're doing is we're actually going to put on GitHub a collection of memory safety errors that we're going to use as a way to define memory safety for the community. So if a compiler can find those errors, then that compiler could be certified as being capable of finding all the memory safety errors as defined by the what's on GitHub. So that's the date for the release. That is the blog goes out on the same time. And then the GitHub source code to define memory safety in C++ will go out around Christmas.
Thank you.
We have a question from online attendees. Is there a vision for an optimal solution for all these types of problems?
I wish I had it. An optimal solution for all of these. The only thing I can come up with is that there would have to be a really good global analysis. And one of the things I haven't talked about is if you spent a lot of time, if you had an infinite amount of time and you had the resources in the cloud, there's no reason why we couldn't do a much better job. And that would be the only time I think you could really approach what I would consider to be optimal performance without the need for many runtime tests. The language just is not memory safe.
Sure. On one of your slides, you had a list of open source projects that you said you were running through this process. I was wondering how you picked those projects, and then you also said there was sort of a backlog of getting that information to those open source projects. Is there going to be some sort of dashboard or some sort of way of keeping track of that?
There's a dashboard that they use to beat us on the head every week. So I wanted to show you that, but they said I can't. So we did put out a blog, and I showed you the link. It's in the slides for the ones that we did fix. We have a team of contractors that are going to use this information to actually go and update all the open source for us. And we just got a contractor 2 weeks ago, so that we now can handle that workload. Because we're deluged with work for open source. We got to finish work for the kernel address sanitizer, kernel mode ASAN. We've got to be able to do all of Office. We've got to be able to do all of SQL. So,
I'm just wondering about the reporting. So, I mean, just reporting those errors to the open source projects instead of fixing them would be helpful.
I would have thought that we did.
Okay, that's what I was asking.
I'm pretty sure. I'm sorry. I'm sure. In fact, that's a good question. I'll go check.
Is it possible to mix and match the continue on error and the full ASAN stop, at least like on translation unit level? Because I would imagine this reminds me a lot of like introducing new assertions into a mature code base, like where you add an assertion and suddenly what used to be working just fails, and it's like it's a benign bug, but we still want to eliminate those. So I would imagine if I want to enable the whole continue on error, then it runs through the 200,000 tests. I fix stuff, and then I would like, for example, for a particular translation unit, to enable hard error if somebody new comes in and fails.
Yeah, you'll be able to mix and mode mix and match. So if you have one DLL that is compiled continue on error, and the other one's compiled. Everything gets compiled first with all the instrumentation, and what establishes the behavior at runtime currently is an environment variable. And I think this is a great question because right now, once you set continue on error in the environment variable, everything goes continue on error. And so we should be able to handle that scenario. So that's really a great question. I didn't think about that.
Right, yeah, it's just some experience we had with just runtime contracts, which is to an extent has some similarity. So we had the assertion facility, and then we introduced what we call review facility to introduce existing code that seems to be working and then we just add the review that just logs, essentially continues an error. And then when we fix stuff, like our clients, then we change it to assert. So any new clients will just, hit the hard error. Right, thank you.
Makes sense. Anything else? If not, please think about how important memory safety is. Not many people talk about it, and I tried to touch on the subject. I can only tell you I had the gift of being in a briefing about a month ago about what Microsoft did to help in Ukraine. And the cyber attacks that the Russians used when they started and when they actually then got much more narrow at different power facilities, memory safety errors were exploited, and we helped. And so I'm kind of proud of that, but that's how important it is. Anybody else? Okay, everybody, thank you very much. Appreciate your time.